You know, our electric power grid is just one of the most ridiculously complex machines we've ever built. It's this massive, sprawling network of generators, transformers, and high-voltage lines, and yet, for the most part, it just works. But that stability? It's incredibly fragile. It doesn't happen by accident. It relies on a whole network of invisible sentinels, little devices that act in milliseconds to stop a catastrophe before it even starts. So today, we're going to pull back the curtain on these unsung heroes, protective relays.
All right, so here's the plan. First, we'll get into the fascinating philosophy behind why the grid is designed to fail. Then, we'll unpack the grid's two-tiered defense system. After that, we're going to get our hands dirty with the mechanics of two classic relays, the super simple magnetic tripwire and the surprisingly clever spinning disk. And you're going to want to stick around, because at the very end, we'll reveal the one beautiful equation that ties it all together.
I mean, it's a totally fair question, right? You've got thousands of miles of wire just hanging out there, exposed to lightning, falling trees, equipment getting old. You'd think we'd have constant rolling blackouts, but we don't. And the secret isn't some magic bullet that prevents failure. The secret is actually embracing it. It's a philosophy that accepts failure as just a fact of life.
And this right here, this is the counterintuitive genius of the whole system. The people who design the grid, they know they can't build something that's literally indestructible. I mean, it would be impossible and cost a fortune. So instead, they build for resilience. The goal isn't to stop every single fault from ever happening. It's to instantly contain the damage the second one inevitably does.
And that brings us to the grid's insurance policy. This whole idea isn't about preventing the accident, it's all about minimizing the chaos after the accident happens. And that is the core job of protective relaying.
So let's be super clear here. A protective relay doesn't stop the lightning strike. It can't. But what it can do, what it's built to do, is sense that massive surge of current from the strike and, within just a few milliseconds, tell a circuit breaker to open up. It performs surgery. It isolates the damaged part of the grid from all the healthy parts, cutting out the cancer so the rest of the system can keep on running.
Okay, but what if that first offender, the relay itself, is the problem? What if it fails? Well, the system has a plan for that too. It's all built on a strategy of defense in depth, with both a primary and a backup system. Let's break down how that works. This slide shows the core strategy perfectly. The grid is carved up into these zones of protection. Think of them as protective bubbles around every major piece of equipment: a generator, a transformer, a power line, you name it. And notice how the zones overlap? That's on purpose. It makes sure there are absolutely no unprotected gaps. The whole name of the game is containment. Keep any failure as small and as local as you possibly can.
So inside each of those zones, you basically have two teams ready to go. You've got your primary relay. That's your first responder. It's fast, it's precise, and it's designed to trip instantly and take out only the single faulty piece of equipment. But if it fails, maybe the relay is offline or the breaker is jammed, that's when the backup relaying wakes up. It's intentionally slower to give the primary system a chance to do its job first, and its response is a little less elegant. It might take out a whole bigger section of the grid, but hey, it prevents a catastrophic, system-wide collapse. It's the essential, if slightly clumsy, safety net.
So how do these little gadgets actually work? Let's start with one of the most fundamental designs out there, the electromagnetic attraction relay. Honestly, the best way to think of it is as a very, very smart magnetic tripwire.
The physics here is just beautifully simple. We all know that electric current creates a magnetic field, right? Well, the absolutely enormous current from a short circuit creates an equally enormous magnetic field. This relay just harnesses that raw magnetic force to physically pull a switch and trip the circuit breaker.
Just look at this. It's like a four-step mechanical dance. 1. A fault sends a massive current surging through the relay's coil. 2. That coil instantly becomes a crazy powerful electromagnet. 3. That magnetic force yanks a metal plunger towards it. And 4. That physical movement closes a contact, which sends the trip signal to the breaker. It is direct, it is brutally effective, and it's all mechanical.
So what's the one thing you need to remember about this type of relay? Speed. Pure and simple. Because it's just relying on a raw law of physics, it operates almost instantly. There's no software, no processing, no thinking involved. Fault current shows up, magnetic field shows up, the relay trips. Fast, simple, and incredibly robust.
But what if you need more than just raw speed? What if you need a little bit of intelligence, a little finesse? Well, for that, we have to turn to a much more elegant device, the induction-type relay.
This quote from the source material is the absolute perfect way to get it. If you have a basic idea of how a simple electric motor works, then you already know how this relay works. It really is just a tiny little motor that, instead of spinning a fan blade, is designed to close a trip contact.
Okay, so how does this little motor actually spin? The fault current is cleverly split to create two separate, interacting magnetic fields. These fields then create these little swirling currents, they're called eddy currents, in this metal disc inside. It's the constant push and pull between those magnetic fields and the swirling eddy currents that creates a turning force, a torque that gets the disc spinning. And as it spins, it gets closer and closer to the trip contact. When it finally touches, boom, the breaker gets the signal. And here's the key. The stronger the fault current, the faster that disc spins.
And that is its finesse. That's its superpower. It can be calibrated so that a small, temporary overload might just nudge the disc a little bit, but not enough to actually trip. But a massive, dangerous circuit, that'll make it spin like crazy and trip almost instantly. This built-in time delay is what lets engineers coordinate hundreds of these things all across the grid, like a perfectly timed orchestra.
So we have the brute force attraction relay, and we have the elegant induction motor relay. They seem like they're from two totally different worlds. But what if I told you that they, and pretty much all relays from this era, are just different flavors of one single universal principle?
And this is where it all comes together. Decades of brilliant engineering, all these different designs, can be boiled down to a single, incredibly elegant formula, the universal torque equation. You can think of it as the grand unified theory for every electromechanical relay ever designed, describing every single force at play inside them.
Now, whoa, don't worry, nobody's getting quizzed here, we are not doing the math, but I just want you to look at the structure of this thing. Don't think of it as a problem to solve. Think of it like a recipe.
Let's look at the ingredients in our recipe. That first term, the one with the I squared, that represents the force you get from current alone. That's the recipe for our simple magnetic tripwire. The third term, the one that combines voltage V and current I, that describes the force you get from their interaction. That's the recipe for a spinning induction disc. And that last little term, K4, that's just the restraining force from a spring. By changing the K values, think of them as how much of each ingredient you use, engineers could cook up any kind of relay they needed. It is truly the one equation that rules them all.
The protective relay is just a perfect example of this invisible technology that makes our modern lives possible. It does its job in total silence, in fractions of a second, preventing disasters we never even hear about. It really makes you wonder, doesn't it? What other hidden systems, what other unsung heroes are working right now, right this second, to keep our incredibly complex world from falling apart?